Thanks for coming. So today we are pleased to have Casey who will be leaving us next week.
Yes.
We'll be back probably.
Sometime, hopefully not too far in the future. Yes. Okay. Ramsey stuff, okay. All right. Yeah, so I'm going to talk about Ramsey numbers of Boolean lattices. So I think everybody here knows the classical Ramsey results. I won't mention that, and I'll just get right to it. So in the poset setting, okay, we say that a poset P is an induced subposet. Some people just call it a subposet of Q if there exists an injection phi mapping P to Q such that X is less than Y in P if and only if phi X is less than phi Y in Q. So it's a kind of injection preserving relations in both ways. If we only had the forward direction, we call this just a non-induced subposet. But mostly for this talk, we'll be talking about induced subposets. So the Boolean lattice well, this can kind of mean a few different things, but for this talk, it's just a power set of an n-element set with the containment relation. So mostly we're not going to care about lattice type operations. It's just a poset. And we define the Ramsey number R, let's say QM, and I'll denote this by QN for, I don't know, the n cube. So the Ramsey number QM, QN, this is the smallest number n such that for any blue-red coloring of Q capital N, we have blue QM or red QN. So these are the key definitions for today.
As an induced subposet.
Yeah. As an induced subposet. So let me start by saying what's known in the general diagonal case. So Axenovich and Walzer, Stefan Walzer, so what did they show? So they showed that 2n is less than or equal to Qn versus Qn, and this is at most n squared plus 2n. So let me tell you how these kind of lower bounds, I mean the basic lower bound goes. It's pretty straightforward. So the easy way to get a lower bound on the Ramsey number of Qn versus Qn is, well, what does this mean? This means that if we take the Boolean lattice on 2n minus 1 things, then we should have some good coloring of it that avoids Qn in either color. So what can we do? So this is Q 2n minus 1. We just need a good coloring. So a very trivial thing would be just, well, it doesn't matter how we do it. We take n levels which are red and n levels which are blue, and just by the height of Qn, the height is n plus 1. We don't have any space for we don't have space for either. So such a coloring shows that Q2n minus 1 can be properly colored. So this is a simple lower bound. The upper bound required more work. Okay, so improvements on this. So Walzer, in his thesis, so I don't know, I'll just write thesis. Actually, we can say Qn is upper bounded by, we don't really need the plus 2n, we can just say n squared plus 1. So it was a slight improvement to the upper bound. And then this was improved by Liu and Thompson, I guess 2019 maybe. They showed that Ramsey Qn, okay, I mean it's still a small improvement. This is at most n squared minus n, maybe there's a plus 2, but basically n squared minus n. So all the upper bounds of this are still something like n squared. And in terms of the lower bounds, well, there's been very little improvement on the lower bound for this beyond the naive one. So it was proved by Cox and Stoli. I don't know if there's 1 or 2L. 2017 maybe. That actually instead of 2n we can say 2n plus 1 is at most that. So there's some slight improvement beyond this naive layered construction. And actually, surprisingly, this slight improvement has generated a lot of attention in that. So this proof was probabilistic, using some local lemma stuff. I mean, actually, they were interested in kind of the general Qn case, but basically the proof is the same for the diagonal case. But actually, for this problem, Tom Bowman, so some kind of famous guy, was also interested in this, and Peng, recently in 2021, they also proved the same bound, same lower bound, but it was a constructive, in the sense that they give a kind of explicit construction that does it. You don't have to do this averaging. And okay, and one result that that we had, which I won't really talk about this one today, but actually we can also prove this constructively. But our constructive proof actually works for non-induced posets. So why is that anything new, well, okay, I won't introduce this notation, but if we say Ramsey non-induced means the obvious thing, so we forbid Qn and Qn in some non-induced way. So, for instance, a non-induced embedding of Qn, we could just take a chain of length 2 to the n, and this would contain Qn in a non-induced fashion, because all the relations go one way. So actually, for this, we get the same bound. So I mean, in general, this is of course upper bounded by Ramsey number Qn. So this non-induced direction is also an interesting thing, but again, not something I'm going to talk about a lot today.
Do you use the probabilistic proof or is it construction?
So I mean, this is a constructive, a constructive. Yep. So this was also, I guess, 2021. Okay. So that's what I'll say about the diagonal case. A lot of these kind of general bounds translate to the Qm versus Qn case, but since even the case of Q2 versus Qn, so a diamond versus Qn, was not really totally worked out. So that's the first interesting kind of non-diagonal case. So let me say what's been done there. So again, in this original paper, Axenovich and Walzer, the same paper, they proved that, well, Ramsey Q2 versus Qn, so this is linear, so okay, maybe not so surprising that this is a linear bound, something like 2n plus 2, I think. So this is a linear bound, and of course we have the same, by just doing this layered argument, we have the same naive lower bound. I mean, the same style of naive lower bound where we just take levels, and if you work out how many levels you get with that, that's n plus 2. So you can take a q n plus 1 and color the levels in this way. So these are kind of naive bounds. I mean, the lower bound is naive, the upper bound was a longer argument. So this was improved by Liu and Thompson in the same paper. So they proved that this upper bound of 2n, actually we can improve it to 5/3 n. Okay. So q to 2n is at most 5/3 n plus 2. This was maybe 2019. And okay, the main result which I want to talk about today is that, okay, we improved this upper bound from 5/3 n to n, which gives the sort of sharp asymptotic. So that was Methuku, Tompkins, 2021. So we proved that Ramsey Q2 Qn is at most n plus some constant times n over log n. Right? So in other words, that means that this function is equal to asymptotically to n. So it's n 1 plus little o 1. So that's the asymptotic for this. Right? Actually, I will remark also it's a little bit interesting in the non-induced case. So if we don't forbid induced posets and we look at Q2 versus Qn, actually the answer, we can prove a lower bound of n plus 3. So this is for non-induced. And actually, n plus 3 turns out to be the exact right answer for the non-induced case. So if you look at the Ramsey number of Q2 versus Qn in the non-induced setting, actually n plus 3 is exactly right. So we don't have this n over log n stuff. But surprisingly, the situation is much different in the induced case. So there was a very recent theorem a couple of weeks ago. I haven't checked the paper in detail yet because it's kind of a long paper. But this was pretty surprising, I think, that Axenovich and Walzer again, but this time in another paper, so 2021, they proved actually that the induced Ramsey number of Q2 versus Qn, this number is actually, let me write it this way, it's at least n plus some function of n over log n. So, in other words, we have that this is n plus the second term is n over log n. So this is needed somehow, which is surprising because when we worked on this, we thought that probably it's a constant, or at least I thought it was a constant, and it was hard to improve by +1 and this kind of thing. But actually, it turns out that this is the correct growth rate of the second term. Okay, so that's those are the main results that are known. So mostly the rest of the day, I just want to talk about this this upper bound and how the ideas of how this proof works. So the proof, in some sense, the general idea is sort of straightforward to understand, but I mean, the problem is when you work it out in detail, there's a lot of little delicate things. But so let me give the sort of proof idea, which contains most of the elements of the proof of this upper bound of n plus constant times n over log n. So proof idea. And as long as we have time, I'll fill in the more rigorous details. But let me give the brief sketch first of how this works. So, okay, so suppose, I guess by way of contradiction, that we can take we can take Qn plus k. I'll tell you what k is in a second. Qn plus k and write it as some partition of red sets. I don't know how we write it. Partition, so red sets and blue sets, such that let me write Qn is, I'll just write this. This means not a subposet, induced subposet of the red sets, and Q2 is not a subposet of the blue sets. So suppose we could do this, and let's take some k so that we get this n over log n. So k is going to be something like Cn over log n. We'll see what C has to be later, but so this is the general form. So we think of Qn plus k, and k is something like n over log n times a constant. Actually, log base 2. Okay. So suppose we have this partition of Qn plus k. We expect that that we will be able to find the Qn of the proper color, or Q2 of the proper color. So, okay, so here's kind of the trick. So take Okay, start out arbitrary. So take an arbitrary permutation of the extra elements beyond the initial Qn that we're trying to embed into. So take a partition, a permutation pi mapping n plus k minus n to n plus k minus n. So we order the extra elements in some way. And the way the proof goes is, okay, we try to construct an embedding of Qn into the red sets of Qn plus k. So we want, in some sense, an embedding phi from Qn into the red sets. But of course, we will see that this will fail because that's what we're trying to show. But we start trying to construct an embedding like this. And more specifically, I'm not going to think of going from Qn to Qn plus k, but try to make the embedding go into a certain subset of Qn plus k, which is going to be useful, defined in terms of the permutation. So actually, is there two L's? Actually, so we define phi. So it's going to go from Qn into the following set. So this set of x union y such that x is one of the initial subsets of the first n elements, and y is equal to the first few things in the permutation. So is equal to pi of n plus 1, pi of n plus 2, okay, pi of n plus I, for some I at most k. So really our embedding just looks at embedding into sets like this. So we fixed the permutation already, and we're looking into embedding into, well, we take a subset of the first n elements, and then we take the first interval from the permutation that we take on the last k elements. So that's the general way that we look at the embedding. Okay, so why is this good? Okay, what's the best way to say it? Second. Yeah. Okay. Let me try to explain how this embedding is going to look. So here's Qn, and let's say we're in the process of defining this embedding. We have a set A in Qn which we're trying to embed. Now, the first candidate of a red set to try to embed this, to try to map this set to, is, well, we have the Qn in the image Qn plus k, so we have this first n power set, and we try to send it to, okay, So this is cheating a little bit, but we try to send this set to a red set here, because basically what we're trying to do is construct a embedding into the red sets of Qn plus K. So we try to send it to A, again over here. So we start out by trying to map it to itself, more or less. But this can fail in a sense that what if when we try to map A to itself, what if the image set that we get is a blue set? Okay, then this embedding has not worked. So now we try to go another step further. So now we take, let me write it as Qn. Okay, I'll write it like Qn plus pi n plus 1. But what I mean by Qn plus pi n plus 1 is I take all of the subsets of bracket n, and then I add pi n plus 1 to it. So I add the first element of this permutation. The permutation, remember, is on n plus k minus n. So now I try, instead of A, I try to go to this set here, which is A union pi n plus 1. So I try, instead of A, I try to throw in the first element of the permutation of the last k things. Okay, so maybe this is a red set, in which case I'm good. But if it's not a red set and it's a blue set, well, I'm still in trouble. I still haven't found the red set I'm looking for. So I keep going further. Okay, so now, now we take Qn plus the first two consecutive things in the permutation which we have fixed already. So we try to go to pi n plus 1, pi n plus 2. Okay, and we try to send it here. Okay, so maybe let's suppose that this is good and we actually land on a red set here. Okay. In that case, we say that the image of A under phi, it's just going to be this red set in this second Boolean lattice, in this, I guess, third Boolean lattice, which we have defined in this way. Now, this phi function is going to be defined in kind of a recursive way, that we map the empty set somewhere, and then we map things larger than the empty set. And it's recursive in the sense that where I try to send each set A to, it should only depend on where I've sent the subsets of A to. So this phi is going to be built up step by step, starting with the empty set. So what do I mean by that? So now, let's say we've already embedded A, and later on we have a set, let's say A prime. And now I want to try to embed A prime. Well, I'm not just going to go to try to embed it in Qn directly. I'm going to look at all of the subsets of A and see which one is the worst, in the sense that I had to go furthest to the right to try to embed this subset. And I'm going to start by going that far when I try to embed A. So in embedding, let's say that A was the worst of the subsets of A prime. So immediately I'm just going to jump all the way to here and try to embed A prime over here. So I'll go over to here. And this set over here, this set is going to be, well, A prime union pi n plus 1, pi n plus 2. So I start by embedding there. And maybe this doesn't work. Maybe I hit a blue set. So again, I'm trying to construct an embedding of Qn into the red sets. So maybe I hit a blue set here, which means, okay, then I have to go one step further to Qn plus, okay, pi n plus 1, pi n plus 2, pi n plus 3. Okay, so I have to go one step further, and then, okay, maybe here I'm lucky and I hit a red set. So this is the general form of the embedding, that I do it recursively, and that at each step I send it, I look at all the subsets of the thing, and I find the subset that had to go furthest to the right. And then this one will start at least that far to the right, and it will be the analogous set that far. Okay, so let's look at what we get by. So later on, as much as we have time, I'll try to do this more rigorously, but let's see what kind of properties we can expect from this kind of embedding. So what can happen? I mean, it could happen that I keep doing this and then I run out. So I'm adding, when I'm trying to embed A prime, I'm adding additional elements, pi n plus 5, pi n plus 6, and so on. Eventually it could happen that I run out of these k elements that I'm trying to embed, and then I still hit blue sets all the way, and I never successfully embed A. And in fact, this will happen because we don't expect to be able to find a good embedding. So if we fail, in other words, as long as we do this, we get blue sets all the way, then we'll just have a failure indicator. So we'll just say that phi A, instead of mapping to some red subset of the Boolean lattice, we'll just indicate that we failed to embed phi A. Okay? So that's the basic structure. Now, what does this mean? Now, let me record a couple of things as I'm doing this. Notice that as I do this embedding, I get a sort of natural blue chain which emerges while I'm doing this, because here I get a blue element, here I get a blue thing, and then, well, this is a superset of this red thing, so I get another blue thing. So if it takes me 5 steps to embed a particular A, then I've generated in some sense a blue chain of length 5. So if I fail, actually in this case, I generate a blue chain of length k plus 1 because I failed all the way. So it's a little bit, we have to be careful about how we do this, but if you do it right, you can show that this will be we will get the blue chain of length k plus 1 every time we fail. So actually this will imply blue. Remember, blue is supposed to be Q2 free. So we will get the blue k plus 1 chain in this case. Okay. Yeah. So it's, the proof is kind of it's kind of a proof by contradiction. So we assume that there is no red Qn or a blue, and that there's no blue Q2. So we try to embed. So we start by essentially trying to embed Qn into the red set. So we try to create a red Qn. Okay, but maybe while we're trying to create this red Qn, well, since we don't have a red Qn, for some set, I mean, we're going to have to fail sometimes doing this, because otherwise we'll have a good embedding of all of Qn. And when we fail in this way to embed A, the result will be that actually we get a blue chain of length k plus 1. We can find it. So
when you choose the file A prime, do you start from the place where file A ends, or do you start from
yeah.
file N plus 1?
So you start from, so when you're looking at A prime, So the embedding is done recursively. So you start with the empty set, then you take only consider a set which contains everything you've already embedded. Not everything you've already embedded, but you take a set where you've already embedded all of its subsets, and then you look at the worst of those subsets, about how far to the right you had to go, and then that's your starting place for the next set to embed. And in this way, you keep going farther to the right, and the chain you will get is it will actually be a blue chain that you generate as you go in this way. Now, I'm not saying this is completely obvious. This requires some proof, but this is the sketch for now of how it goes. So in essence, what's happening is that so we fixed a permutation pi, and we've tried to embed Qn into the red sets. We know we have to fail, and then we know when we fail, what we will find somewhere is a blue k+1 chain. So okay, so let me just write it kind of schematically. So we have initially fixed a permutation pi of the last k elements, and from pi we found some a which fails in the embedding. So we found some a, so that as we denoted it, phi of a equals star failure operation. Okay, so so some a has failed, but then we see by recording this blue chain as we go that this will yield some blue k+1 chain. And actually, just by the definition, the form of this blue k+1 chain, it will look like something like, it will be some set x1, let's say. x1 is a subset of 1 through n, and it will just be like that. And then the next thing in the blue chain, it will be some set x2 in the first n elements, which contains x1. But then moreover, we've added in pi n+1. So we've added in one of the extra k+1, the extra k elements. And x3 then is the same. It will be some superset of x2, and we've added in pi n+1 and pi n+2, and so on. So we generate a k+1 chain in this way. So basically what happens is, so we have a permutation pi, and then we find some a, so there exists a, so that we fail because we aren't going to be able to embed, by assumption we can't embed red Qn. But then this failure yields a certain k+1 chain. Okay. So the next observation is that now we have this blue k+1 chain, and it is of this form where we're taking supersets of the first n elements, and then we're adding incrementally consecutive elements of the permutation of the last k things. So in this k+1 chain, focus on the top and the bottom. Focus on the top and the bottom elements. So let's consider then, let me just write it this way, the bottom element and the top element. So just narrow in on these two. So in essence, for each pi, we can generate some top and bottom element of a blue chain, which has, and the blue chain has this kind of structure. Okay. Now, actually, this is almost the end of the proof sketch, I guess, because now, what does this mean? Okay, so let's look at these bottom and top elements. Could it be that pi and sigma, let's say, two different permutations, give us the same two top and bottom elements. So let me write it this way. Could we have bottom with respect to that we get from permutation pi, and the top, which we get from permutation pi, equal the bottom, which we get from permutation sigma, and the top, which we get from permutation sigma. So can we generate the same top and bottom element from this blue chain for two different permutations, pi and sigma, of the last k elements? So suppose that we had this, okay? So this bottom set is the same. So now this is some set in 2 to the n plus k, in qn plus k. So this is the bottom element. So this is the bottom. We have the top set, top. Now, we have these chains from here to here, right? But let's look at the first position in which pi and sigma differ. So take the smallest j, let's say, so that pi j does not equal sigma j. Okay? And look at the structure of these chains that, okay, we're taking supersets among the first n elements, but then we're taking just increasing intervals along this permutation. So in this first place, when these differ, we will have, okay, so maybe the chains agree for a while, but definitely we will have these sets where along one of the chains, this thing has the jth element here contains pi j and not sigma j, and the other one contains sigma j and not pi j, right? So these two sets along the permutation will have to be incomparable, okay? And the result of that, if we have between the same bottom and top element, if we find these two blue sets which are incomparable to each other, well, this is exactly an induced diamond in the among the blue sets, right? Because we have a top and a bottom and two things which are incomparable in the middle, so this is an induced diamond. So what does this mean? This means that for each permutation we take, when we do these operations, the bottom set and the top set that we generate will always be different. So it's a kind of injection. So what this means is that, so if we look at permutations, the set of permutations pi from n plus k minus n, and then we look at, well, these bottom and top sets are both elements of 2 to the n plus k, right? I mean, so this is 2 to the n plus k cross 2 to the n plus k, right? So this will be an injection under our assumptions about not having a red qn or a blue q2. Okay, and now it's just a small computation because, well, how many permutations do we have here? Well, this is k factorial. Okay, and how many pairs here? This is 2 to the 2 n plus k. Right? So we know because there's an injection, this has to be bounded in this way. So the right-hand side is because the number of pairs, this is, I mean, it's a kind of a naive bound, but we're just looking at the bottom is some element of 2 to the n plus k. It's some. No. The bottom element is Right. You want to improve it to say
I just wonder whether you need the K in the
I think you're right that maybe we can say here we definitely need the 2 to the n plus k because
the top always contains all the last K. But is that not affected about? It doesn't.
Yeah. I think you're right. I think we can write 2 to the n cross 2 to the n, but it won't matter on the bound. But yeah. Okay. Yeah. So now let me briefly show why. This is just a computation, but then why is that good enough under our assumptions? Okay, just erase that. So, okay, so right, so k factorial. This is strictly bigger than if we write k over e to the k. And now let's just write this as a power of 2. So this is just 2 to the power of k log base 2 k minus log base 2 of e. Okay, so here's a way to think lower bound k factorial. So here we have it now in terms of a power of 2, and we know the upper bound is, well, the way I wrote it was 2 to the 2n plus k, so maybe let's just keep that for now. So this means that k log 2k minus k log 2e, it should be less than, I guess, strict, than 2 times n plus k. Okay, just by comparing the exponents. But okay, this we can rewrite. This is just 2n, factoring out the n. This just becomes 2n 1 plus little 1, because k is like n over log n. So if we factor out n, this becomes 1 plus little 1. So that's the form of the right-hand side. But k log k is just, well, this was cn over log n. And then let me just expand out the logarithm. So expanding out the logarithm, plugging in cn over log n here. This is just log base 2 of c plus log base 2 of n minus log 2 of n. Right? So we have this equation. But from this equation, okay, if we multiply this through, the log 2n's cancel with the log 2n. This cancels. I mean, if we multiply it through, so this is, I mean, this is just cn times 1 plus little 1. Okay. So basically, what we get is that huh? No log n, because this cancels. The log n cancels when we multiply. Yeah. So if you think of it as just factoring out cn from these three terms, the only survivor in a sense is this, because the log n and the log n here cancel. So this would mean that c times n 1 plus. So what we know is then that this has to be smaller than 2 times n 1 plus little 1. But as long as we've chosen c to be some number strictly bigger than 2, and n is large, then this is a contradiction, right? So that's the sketch of the argument. Okay, so yeah, time definitely goes very fast in these seminars. I was going to start rigorizing this proof to more degree, but 7 minutes. Okay, then I can let me say something at least. So let me at least maybe write down what is the. So let me try to formalize this. Okay. So let me just write down the formal claim that we prove about this embedding. It's actually not very hard to prove. So here's what. So this will be the end of the proof, and now here's the replacement of the beginning of the proof. So given, so we have some permutation pi mapping n plus k minus n to n plus k minus n. Okay. So what makes the induction go through is there exists functions. Okay. Well, what functions do we want? So we have a function phi from Qn into the red sets, or the failure element, which means we failed to embed. Okay. Then we have some counter which tells us how long of a blue chain we've created so far at each step. So we have some alpha, which indicates for each set we try to embed how long of a blue chain we've generated. So this will be from Qn, and this will go from 0 to k plus 1. K plus 1 then just remains stationary. This is basically equivalent to the star situation here. It means that we failed to embed. And then finally, the most subtle thing to deal with in all the technical proof here is that we want to have some function f which actually defines the blue chain as we go along inductively. So there's a function f which maps Qn into a chain, okay, the weird notation, but into it, this means a chain of length at most k plus 1 in the blue sets. So this will kind of record for each set A how long of a chain that we have. And then this will satisfy some properties. Okay, so it will satisfy property 1. I mean, basic things that we want, that if phi A and phi, so for any A and B, if phi A and phi B are red sets, then we want to have if B is a proper subset of A, if and only if phi B is a proper subset of phi A. That's the property we want. We want a property like if B is a proper subset of, let's just say, any subset of A, then we want that alpha B is at most alpha A. So this is kind of increasing. This is property 3. Did I write down property 3? I did write down property 3. Okay, and if it happens that our length of the recorded chain so far, if this is k plus 1, then we want 5a to map to the failure element. And then this is kind of key. If otherwise, let's say, otherwise, well, what we want to be true is that where we map A to, it equals, so if we only look at the first n elements, it equals A itself. So it does what it's supposed to do on the first n elements. And then if we look at the remaining elements, so 5a minus n, this should just equal pi n plus 1 up to pi n plus alpha a. So remember, alpha a is recording how long of a bad chain we've created so far. So we have this kind of property. And then we have properties, so that indicate what kind of things the chain is supposed to satisfy. So for all a, Qn, so the chain fa, which we generate, it will be some chain that looks like, let's say it has the first element, fa1, and the chain will have length alpha minus, the chain will have length alpha, so it goes up to fa alpha a minus 1. So indeed, the alpha records how long of a chain, and these are all blue. These are all blue sets. And in fact, what we want is the ith member of this chain that we've created. If we throw away the first n elements, this should just be the auxiliary elements we added, n plus 1 up to n plus I. Okay. And P5. This one is also maybe just more technical to make the induction go through. What we want is that for all a, the last thing that we get in the chain that we've recorded, so f of a alpha of a minus 1, so the final element of the chain we recorded, we actually want this to be a subset of a itself. So this is the properties we want, and the way this is done is that these these things are done recursively, and that we can do it for the empty set, and each set we consider, it only depends on the things below it. And as we're doing this, we prove these properties by induction, assuming that it holds on all the things below it, which we've defined. We now show it holds for the current thing, and that lets it go through for the entire thing. But yeah, unfortunately, I think there's not really a lot of time to go into the details of how this is done, but the basic idea is this picture which I drew. Maybe I just make one remark in terms of going further. Back to the proof idea, one direction that initially seemed like a good way to go further with this idea and try to generalize the Q2 Qn result to a Q3 Qn result and so on, is that what is really happening here? How do we, did I delete that picture? Yeah. How did we get to this bad diamond situation? We had these two permutations that, well, at position J they differed, and then we can see that the two sets we got each had an element which the other didn't, so they're incomparable. So this let us generate the diamond. So more or less, if we want to try to generalize to R, say Q3 versus Qn, basically the only thing that's missing in the proof is that we would have to show that now, so here, basically we're taking two chains. We're basically taking two chains in the set 2 to the power of k, because we're only interested in these last k elements. So these are two maximal chains, a chain containing each element in this. So, and what we see is that if we take two chains in the last k elements, well, if they differ, they will differ somewhere, and that's already enough to force an induced Q2. So to push the argument further, it would be interesting to know that if we look at chains, maximal chains in 2 to the k, how many maximal chains in 2 to the k do we have to take in order to force an induced Q3? So we just union. And you can have a lot. I mean, it's not going to be like 2 or something like that. I mean, it's going to depend. It's going to certainly depend on k. You can do a kind of grid pattern, and there's many ways to avoid a Q3. But I'm not sure exactly what upper bound you would have to prove, but you have a pretty big range of an upper bound you can prove that would that would push this to Q3 versus Qn, but we thought about that a little bit and we couldn't really do it. It seems promising. So
About Q3 versus Qn.
So my belief, I don't know if Abhishek and Dániel agree on this, but I expect that for any fixed Qm, as n is large, I would expect that n is the correct asymptotic for everything. But yeah.
Where is the Grósz superlinear n?
I think it will be only if m is a function of n. I think for constant, I expect that for constant m, if we compare Qm versus Qn and let n be big, my feeling is that it should always be asymptotically n. But I don't know. That I have very little intuition. That's a very strange. I have no idea if it's like n squared or if it's like n. It's difficult.
Q2 versus Qm, what is the constant in front of n over log?
So if you take n, if you allow n to be large, then as we saw here, you can take any any positive constant bigger than 2 is sufficient, and then you can take large enough n, it works. But if you try to optimize it so it works for all n, it's 6.14. It seems is what this proves. But I certainly haven't checked this recent paper in detail, but I saw 1 over 15 written a lot of times, so maybe that's right. So it's a big. I think it's a big gap.
I think you can improve this too. Maybe because this should be the number of pairs should be comparable sets to the 2 to the n. Because the bottom of the chain is an element of 2 to the n, and the top of the chain is a superset of that guy plus the last big element. I don't know. Maybe it's wrong. And it's only in the constant.
Yeah, I agreed with what you said before. I mean, it seems like you can improve a little bit, but it didn't really seem to. It seems that.
How many comparable pairs are there in the Boolean lattice? It's not 2 to the 2.
It's like 3 to the n.
Some k times n just k is 3 to the n. Is it? 2 to k times n? I think 3 to the n.
So maybe improve it to.
Yeah, I mean, like I said, that. Yeah. I mean, it would be very interesting to get the exact constant maybe now, but I think that would be pretty hard.
Like multiple, so three cards, let's say Q2, Qn. Then can you still then have some
Yeah, I don't. We didn't look at that close. Some of the papers on this involve more than 3 colors. I think that. I think that you can add as many a constant number of Q2s and Qn. I think it will still be n asymptotically, but I'm not entirely sure.
All right. Any other questions? Okay, let's thank